Thanks everyone for joining here today. So yeah, I'm really excited to introduce Professor Gabriel Katul, who is joining us today from Duke University. But I've recently learned today that he is on the move to the University of Alabama in a new and special position. So congratulations to Gabby for that. And so this seminar series is in honor of a former faculty member in this department, CCMA. And so we're especially excited to host Gabby for this distinguished seminar series in CCMA's honor as well. Gabby will tell us about peak water as a driver of peak grain for the U.S. High Plain Aquifer. But I want to tell you a little bit more about why I think Gabby is such a fantastic speaker in general, but also a great fit for this distinguished seminar series. So Gabby has his bachelor's from the American University in Beirut, and then he came to the United States for a master's at Oregon State and then a PhD at UC Davis. And he's currently distinguished professor in hydrology and micrometeorology at Duke University. And he's got such an extensive list of awards I won't bore the audience by listing all of them. But I think what I've been telling people during his visit today is that Gabby is perhaps one of the best people in the world to be able to have a technical, detailed conversation with every member of the faculty in the Parsons lab. And I think that's very impressive to be able to speak to the hydrologist, the fluid dynamicist, to talk in detail with me about turbulence, and then to talk with Darcy about phosphorus and so on. I certainly can't do that, so I'm very impressed by that breadth and depth of research as well. It's not just a wide coverage, but it's also very deep. So I'll just briefly mention some of these awards that highlight some of that element. So he has very prestigious awards from AGU, from AMS, and from EGU. And he was elected to the National Academy of Engineering in 2023 as well for his contributions to eco-hydrology and environmental fluid mechanics. So I'll stop talking. I'll let Gabby take it away. So thanks so much for being here.
Thanks very much for this introduction. It was one of the best, actually. So thanks again, Michael. The title uses a familiar concept of peak oil for exploring grain production from sourced from groundwater. And this topic started as almost as a hobby topic that emerged from a meeting in Etzensburg near Goethe's house. In fact, there was a meeting in eco-hydrology and sustainability research in Germany. At that time, if you're wondering why half of the presenters from the US were there, it turned out to be to have a meeting in a prestigious place, and UNESCO heritage site was cheaper than to have the conference at University of Delaware. So we decided that we would pick that option and have the meeting there. And during that meeting, there was a lot of discussion about connections between eco-hydrology and sustainability. And it became clear to many of us during these discussions that there was no overarching theory to be even developed. And so we were thinking about ideas that could be used. And the idea of peak oil and analogies to peak oil popped up, but it was clear that it was just simply analogies with no mathematical basis. And so we thought at the time with my student, Asad Murad, that perhaps this is worth exploring a little bit in greater detail to see if there is a way to mathematize a lot of these ideas that were thrown around. And so the talk is really about that. The concept of what I would say peak oil, so what is peak oil? Peak oil refers to the point when oil production ceases its upward climb and begins to irreversibly decline. It was first proposed in a report to the Shell Development Company by the geologist Marion King Hubbard in 1956, and it was really an analysis of the available oil production data across the US. And he was showing that at the time, there is a possibility of seeing a peak oil production limit and then, of course, a decline. And so the root description, the mathematical description behind it turns out to be an empirical bell-looking shaped curve. It was really proposed in the analysis of oil production in the US with the thinking that this might actually be a finite resource. And so that's going back to the sustainability issue. So Hubbard reasoned that after fossil fuel reserves, whether be they oil, coal, or natural gas, are first discovered, production at first increases approximately exponentially. The idea is that, well, the easy oil access you will find, and then by investing a little bit more, you can you can extract more, and so that generates returns that allows you to reinvest and harvest more, et cetera. And so you could see that this is going to go exponentially up to a point when further extraction becomes very expensive. And so the cost of that extraction of deeper oil, for example, becomes prohibitive. And at that point, peak output production is going to be reached and begins its decline. Again, in the limit, it will be also an approximate decline. So these were Hubbard's reasoning. If we were to try to summarize it from very familiar concepts in logistic equations, the idea would be something like that. So if you start with a resource amount that can be economically extracted at any time t, and you call that resource R of t, we're at MIT, so it's okay to use a little bit of math, no? And then we can argue that, well, if this resource is finite, it has a maximum value. Let's call this R max. So the extraction rate is nothing but the time rate of change of that resource, so that would be dr dt. And Hubbard's reasoning now can be expressed simply as the production is proportional to the resource, so let's call this omega times R. And that would be the exponential rise piece. But that means that the resource is far from being, feeling the finite value, if you will. But once the finite value is beginning to be reached, it immediately acts on the production. And so there is no delay, basically, between the action of the finite resource effects on the production. In fluid mechanics, this is very common. So if you look at pressure terms in the governing equations of fluid motions, if you open the door of your bathroom very rapidly and you look at the water level fluctuations in your toilet, they will occur almost instantaneously. Okay? So there is no delay. And so here, the thinking is that the finite resource effects are acting instantaneously on the production. So as R begins to approach R max, the production will begin to decline, and the decline will also be exponential. So as R begins to be close to R max, you could replace R with R max here, bring the R max up here, and a little bit of algebra will show you that P is now proportional to minus R, but with the same time scale. Okay, so there is only one time scale in this problem, which is omega. Okay? And that's simply due to the fact that the carrying capacity effects or the finite resource effects are operational instantly on the production rate. So Hubbard then solved this differential equation or proposed this functional form for the solution. And that's no surprise. That's a first order ODE, so you could do this on the fly, I guess. And then what you find is that this differential equation will have a production term that has three unknown parameters, P max, omega, this time scale, and the time to peak. Okay? So these are really the three unknowns. So you need three parameters to describe it. And basically, it also shows that the solution is going to be symmetric. So the exponential rise and the exponential drop are mirror images of each other around maximum production divided by 2. And it is important to emphasize that Hubbard's analysis is not about oil volume or oil mass. It's about extraction rate. So it's about the rate, not the state. Okay, that's very important because there is a little bit of confusion about these differences. So with this insight, Hubbard, in his 1956 famous report, used data sets from 1860 to 1948 about US crude oil production in thousands of barrels, this is shown on the y-axis, against time on the x-axis, and he fitted, almost by eye, this function from 1860 to 1948. The report was published in 1956. At that time, you had, it takes a while to write this report and do the analysis and the regressions and all of that. So he did that, and then he made the projection of what's going to happen based on this data set, what's going to happen to the future US oil production, and found that there will be a peak in the mid-1970s. So that's peak oil in a nutshell. It's about production itself. And then there will be a decline. Okay? Now, he also, because he was using this logistic function, it was very clear also that this description is quite symmetric, okay, around the peak. Now, what happened in reality is that the data set matched Hubbard's prediction all the way until the early 2000s, okay? But then something happened, okay? Something happened that caused deviations from these predictions. And those turned out to be what we now call a technological disruption, okay? This technological disruption came about from tight oil and to a lesser extent, shale oil. So basically, advances in fracking and horizontal drilling allowed us to extract economically oil that was not available before in Hubbard's analysis. So there was almost like a new pot of oil that became available that was not available before because of this technology. And there are two take-home messages from the success of the prediction of peak oil and the failure due to technological disruption. The first point to make was actually made by Hubbard himself just after those predictions materialized. This is a 25-year prediction. Yeah, this is pretty impressive today. If you can forecast something 25 years ahead of its occurrence, it's almost like you have a crystal ball. Okay, so you know that's a great, so to speak, success of data science in a nutshell. Okay. So this prediction was made and it materialized, but it also failed in much later future. So the first message about the successes came from Hubbard himself. So in 1976, shortly after peak oil materialized, he wrote a chapter with a very interesting title. It's called Exponential Growth as a Transient Phenomena in Human History. So that was pretty interesting. But it didn't sit very well with Wall Street crowds, okay? But this is what he said in that chapter as a summary. During the last 2 centuries, we have known nothing but exponential growth. And in parallel, we have evolved what amounts to an exponential growth culture. Very true, yeah? A culture so heavily dependent upon the continuous of exponential growth for its stability that it is incapable of reckoning with problems of non-growth, which is quite true for the financial sector today. Okay? Now, talking about the financial sector, let's talk about the failure of Hubbard's prediction. When peak oil materialized, there was some quietness, but when it failed because of technological disruption, the Wall Street journals had a feast, basically. Every couple of years, they would write an editorial or an opinion, and these are just snapshots from the titles. There will be oil, we are assured. Peak oil demand isn't on the horizon, OPEC says. Peak oil debunked again. Why peak oil is a myth. Okay, so you get the flavor. And to some extent, even more serious journals started looking into peak oil 20 years later. Was it a failed prediction or useful insight? So this came from Hugo Bardi, a very thoughtful person. And basically, you know, the idea is that, yes, you cannot predict technological disruption. These are phase transitions. The data alone will never enable you to predict a phase transition that was not observed, period. You know, there's nothing else to say. So in this sense, Hubbard's analysis, because of its success to predict peak oil, but not, of course, technological disruption, is used as a theoretical framework to analyze other non-renewable resources. These include coal, copper, phosphorus, uranium, you name it. And there are similar controversies that play out very similar to peak oil. And also, this analysis of Hubbard was extended to slowly renewable resources. So the idea is that if extraction rates far exceed replenishment rates to a leading order, you do have basically a non-renewable resource if this is what's happening. So this was kind of the impetus to think about water and grain in this so to speak, context. And that was certainly true. The idea of extending these concepts to freshwater withdrawals and use came about from Peter Glegg and Meena Palaniappan in their inaugural issue of Sustainability Science. This was a new journal that just popped up in the proceedings of the National Academy of Sciences. They introduced the concept of peak water, and basically they were thinking about freshwater withdrawals, of course, geographically located, not on a global level. Water is experiencing what is called the hydrologic cycle, so that doesn't follow the same rules. But locally, you could be extracting groundwater way faster than replenishment. And independently, in the context of food, Lester Brown published a book called Could Food Shortages Bring Down Civilizations?, where he also makes arguments very similar to the ones about peak oil. So in both cases, they were used somewhat metaphorically, if you will, to spark debates about sustainability issues very much similar to what peak oil did with energy. So now we come back to our talk. So what do we want to achieve in this talk in particular? So the first question that we would like to address is, can the concept of peak oil be extended to represent depletion of groundwater in regions where replenishment is too slow? So that's the first question. The second question is that, does grain production sourced from groundwater follow a Hubbard-like curve? There was no empirical support for this statement other than a speculation by Brown in his book. And at least on a slightly academic level, can a coarse-grained theory, not very detailed, but can a coarse-grained theory be derived to link groundwater withdrawals to grain production? And what are its predictions for grain production into the future, say 2050? This is a typical year that climate projections are made towards or heading towards. So these are the questions that we seek to address. But I would like to frame them slightly differently. Is the Hubbard concept simply a metaphor, or is there some mathematical basis for its usage in representing groundwater-sourced grain production? And the reason answering these questions will be helpful is that it may allow us to formulate early warning signals for food security from a dynamical systems perspective, and therefore perhaps be able to predict certain things that could not be predicted from data alone, as I will show. So now, I need to be clear about the approach, because that's also important when we are dealing with issues that involve so many societal complexities. I would like to be able to draw some boundaries about what constitutes a limit of a successful model, okay? Or what would be a successful coarse-grained theory. And in this case, I'm going to actually use the concept of model as proposed by one MIT professor in the early 1980s. And that professor turns out to be a professor of mathematics and computer sciences. His name is Seymour Papert. He wrote a book in 1980 that is very difficult to read, by the way, but full of ideas, okay? Full of ideas. And this book is called Mindstorms, Children, Computers, and Powerful Ideas, okay? That was the title of the book. And in it, what Seymour Papert was trying to understand is how to teach computers to think. That was now what we call, yeah, you know what, artificial intelligence, machine learning, etc. So this was already happening in the early 1980s. And his approach is, well, how do children conceive information? There is a model behind it, okay? And by representing this model, they could then understand the world and be able to even make certain not predictions, but certain conjectures about how it operates. And so in it, he actually introduced a word that I was not familiar with before. He introduced conceptual models. He said that they must be understood in what he called mind-sized bytes. In other words, you cannot have a very complicated model and think you could understand it. I mean, yeah, sure. If you have a model with 100 variables, forget understanding anything, okay? But a simplified model that actually kids use to reason might be understood, yeah, if it has this ingredient of mind-sized bytes. You could bite and chew on it and be able to swallow it without choking, okay? And then he actually goes further and says it's a gross misunderstanding to think that models can predict the future. So he was already, discarding the idea that models are strictly predictive tools, okay? But he goes further and offers this view on models. Acting on the results of a good model, it is always possible to work in the direction of a better future. So in his view, models can affect the future, and that would be perhaps certainly true today with climate models, okay? That somehow, if you are working towards a better future, well, you are informed by a good model that you should understand. And that was kind of his last point, is that to use a model wisely, one must be able to understand it. So it is with this framework that the grain production sourced from groundwater is going to be analyzed. This is not going to be a talk that is going to help policymakers say anything, but it would help us understand this very complex problem in mind-sized bytes. So that's the goal. Okay, so what do we know about groundwater depletion? Well, simply put, this diagram speaks for itself. So groundwater depletion are often measured as withdrawal minus recharge. No surprise, if the withdrawal is far exceeding the recharge, you could think of groundwater as a non-renewable resource, okay? And if you look at the recharge rate globally, the map on the top left shows that. So you could see that, yes, it's very spatially variable. If you look at the withdrawals, clearly you could argue that they are concentrated in certain regions. If you go to where these regions are, you could see that they're actually concentrated in 4 major aquifers around the world. The Ogallala aquifer is one of them. The Arabian aquifer is one of them. The Indus aquifer is one of them. And the North China is one of them. And if you're thinking about where is that water going, well, no surprise. That water is actually going to grain production, food production. And a figure that actually supports this is this figure by Stefan and co-workers in 2010, where they actually showed the percentage of irrigation sourced from groundwater. So for example, if you look at most of these areas, especially in the Ogallala aquifer, you see it's almost 80 to 100%. So the majority of the water is really going towards grain production. Now, the focus of this talk is going to go into the Ogallala aquifer, not because the other aquifers are not important globally, just to be clear. It's just that there is pragmatic reasons. There are plenty of data on both grain production and groundwater levels in that area. There is also a climatic gradient from north to south that's going to help us tease apart the signal of recharge due to climatic changes on it. And last is it's a simpler aquifer to deal with because it primarily deals with groundwater quantity, whereas in the other basins, we have to think about groundwater quality as well. So this offers us a simplified view when water quality is not as crucial as water quantity. That is not to say that water quality is absent, but it's not the leading order term in this analysis. Okay, so what do we know about the area there? Well, if we think about the High Plains Aquifer, sometimes known as the breadbasket of the US, let's start with what has been documented as water level changes going from north to south. So for the purposes of this analysis, just because the grain production data comes by state and different states report it a little bit differently, the High Plains Aquifer is decomposed into a northern High Plains, a central High Plains, and the southern High Plains. And the northern High Plains is going to be represented by the state of Nebraska. The central High Plains is going to be represented by Kansas, and the southern High Plains is going to be represented by Texas. Okay, so the data sets that are representing these climatic regimes are coming from these three states. So if we say northern High Plains, we mean Nebraska. Southern High Plains, we mean Kansas. Sorry, central, and then southern High Plains, we mean Texas. And so this is basically the water level changes that have been documented from 1950 to 2007. So if you look at the data sets here, you find that, in fact, in the northern High Plains, there is gains. Okay, so the water level seems to be going up, not down. Okay. If you look at the central High Plains, there are regions where there is large depletions, but certainly by the time you move to the southern High Plains, water level drops are huge. I mean, more than 50 meters. This is not trivial at all. Okay. And these are, of course, over a period of 1950 to 2007. So this is quite substantial. Now, the recharge rate in those areas is also interesting. And remember, depletion is really the imbalance between extraction and recharge. So let's see what the recharge says. In Nebraska, the recharge is quite high, in fact, in millimeters per year. It's, on average, it could be somewhere along the lines of 50. If you go to the central High Plains, you're beginning to see that the recharge is dropping. And definitely by the time you hit Texas, the southern High Plains, the recharge rates are quite low. So the probability of non-renewable resource or Howard-like looking behavior is likely to be in the southern High Plains, in Texas, whereas in the northern High Plains aquifer, perhaps the issue of non-renewable extraction is just not relevant. And any theory to be developed has to match these expectations, these logical expectations. Okay. So that's what I wanted to say about this basic idea. So now let's go to the model. What is the thinking behind the model? Well, if there is a field where mathematical biology has proven to offer laws about thinking about problems, it's the population dynamics mathematical theories. And this is basically a predator-prey problem. So the thinking here is that if we envision groundwater as a prey, okay, and we envision grain production as a predator that we are facilitating, of course, then we might be able to use ideas from predator-prey theory to offer this type of model. So the model is based on the following. Just as predators and prey respond to changes in the other, the mathematical model that we're going to talk about allows for feedbacks between the costs of shrinking groundwater resource as the groundwater depletion occurs, it becomes more expensive to extract it, and the profits of agricultural outputs. That's, in a nutshell, what the coarse-grained theory is going to try to achieve. And, predator-prey, these are, if there is an area where dynamical systems has proven to be effective, is that it showed us how very simplified differential equations coupled can exhibit quite complex behavior. Yeah? The Lorentz system is one example with 3 differential equations. Limit cycles, of course, can happen with 2 differential equations, and those exhibit self-sustained oscillations. So that's basically the idea behind it. And in the case of non-renewable resource, we will see that it looks like a predator-prey, but without the oscillations. Okay. And so the overall, the model is going to produce for us, in the most simplified version of it, two curves, one for groundwater depletion or use over time, and the other one would be the total amount of crop production over time. So that would be the simplest prediction of it. And the question that we will ask is that, do they look like a Hubbard curve or not? So that's the first thing. Are they two independent Hubbard curves, or are they coupled? And if they're coupled, what type of coupling ensures some, so to speak, truthfulness to the data? So that's what we're going to try to do. And so our thinking then is that we would like to see something that looks like this. We would like to see some sort of a curve for production of water from aquifers. So that would be the black curve. Does it have a peak or not? That's the first thing we're going to ask. Is it symmetric around that peak or not? Okay, so these are clearly some important questions. If it is symmetric around the peak, well, it's straightforward Hubbard thinking, just like peak oil. Okay, but if it is not symmetric, what is the symmetry breaking term? Okay, and then we're going to repeat the same exercise for grain production. Is it symmetric or not? Does it have a peak? And then is it tied in some way to groundwater depletion? Okay, so that's where we want to go next. And here we're talking about grains. We're going to sum corn, sorghum, soybeans, and wheat together. We're not going to distinguish between them, even though over time the stoichiometry, if you will, of these crops have changed. But for now, we're just going to treat them as one aggregate. OK, so now the mathematical model itself. So the way we're going to think about this problem is as follows. We're going to have two compartments, one for accessible groundwater and one for annual grain productions. So one is shown in blue to indicate water, one is shown in green to indicate crops. And we're going to start by saying, if there is crop production, there must be some extraction of, let's say, economically viable water to extract. So that would be the first term in this differential equation. The second term is a recharge rate. So it says that if there is a certain recharge rate associated with that area of the High Plains aquifer, this aquifer is somewhat unconfined, so the recharge rate is easy to think of this way. Multiplied by the area, then that will be the recharge rate itself. So here the thinking is that irrigation is happening in the location where you are injecting well and extracting groundwater. So there is no shipping of water. Yeah? So it's very expensive to ship water, let's say, quite a bit of distances. So it's a localized balance in this case. And then, of course, there is the expansion of your irrigated area. So you could install new wells, and that gives you more access to water. So that's the source term on the irrigated surface water. So you're increasing, basically, the area of irrigation, dA dt, and that adds to dW dt. The annual grain production, which is, in fact, our predator, well, what is a loss for accessible groundwater is going to be a gain for crop production in a similar nonlinear fashion through this interaction term, but there is a certain depreciation that has to be kicked in. If you produce too much crops, yeah, the value of the crops will diminish, and so that's a depreciation value. That's going to be assumed linear. It can't get simpler than this. You could also think of this depreciation rate at multiple scales. So you could think of it from an economic perspective, but from a practical perspective. If you take a field and you increase a lot your, so to speak, crop density, yeah, so number of plants per unit area, you will have internal competition, okay? So that creates also an equivalent depreciation term, competition for water or competition for light, yeah? That's actually the worst competition you could think of because there are no niches. They're competing for the same niche. It's the most destructive competition, the most intense, in fact. And in fact, it's this type of competition that sometimes generate power laws between mass and spacing. You know, it's known as the self-thinning rule, if you're wondering about that. Yeah.
Question about the interactive terms.
Yeah.
The choice of it being a nonlinear product of the two, is that necessary or is done by choice to fit a certain mathematical model?
So the thinking that went into it, first is there is a literature on that if you increase one and not you have to decrease the other. So they have to be negatively correlated. And that's the simplest model you could think of. They could have been power laws. You could have had CW raised to some power. Qualitatively, they shouldn't change the dynamic too much as long as this inverse correlation is imposed on the interactive effects.
But this is not the only way by which you could represent those
No, not necessarily. But the upshot of it is that you want to ensure that depletion occurs when you produce grain. Yeah, that's basically what you want from the model. So it's not the only, they could be multiplicative, they could be C to the A, W to the B, okay? Or it could be CW to the B.
There is no empirical evidence for preferring this form of relationship than others.
So the empirical evidence is going to come later. Okay. I mean, that's one test on the model. Does it reproduce correctly the interaction? And there are the recharge terms, so there is a source term here, and then in the case of the crop budgets, there is a sink term. Okay, so this is in a nutshell the model. Okay, it's really simple. It can't get simpler. I mean, you have stripped it to the basic ingredients. You cannot get simpler than that. There is interaction. So these are gonna be symmetric. Yeah, they look alike. So it can't get simpler than this. So if there is any symmetry, it's gonna be because of those terms. Yeah. Okay, so with this in mind, let's just look at first few other things about the High Plains aquifer and the climatic gradients that was just mentioned, going from the north to the south. So if you look at the harvested acreage areas, or acreage, for Nebraska, it's still going up. So basically, Nebraska is still seeing growth in agriculture, basically, in irrigated farming. Kansas, which is the central High Plains, has already flattened out to a leading order again by 1990 or so. So there is no more new drastic expansion that is happening. And for Texas, for the same period, more or less, it's flat. Okay, so these are the simplifications we're going to make. Okay, so the irrigated acreage for Texas and Kansas after let's say year 1990, there's just this extra source term in our water budget is just not going to matter. But in the northern High Plains, there is still expansion. It's beginning to flatten, but there is still expansion. Now, the recharge rate, again, we're going to assume this recharge rate unrealistically, unrealistically, to be 64 millimeters per year, constant over this period that we're going to do the analysis, not changing, which is not realistic. But again, the important point is the gradient from north to south. Recharge is high in Nebraska, middle in Kansas, low in Texas, okay? The volumes of water are also dramatically different. The water stored in the northern High Plains is 2,600 cubic kilometers. In the central High Plains, it's about 395 cubic kilometers. And in the southern High Plains, it's 41 cubic kilometers. So just the volumes themselves are also important. And those are going to play a role when you start thinking about remote sensing products and sensitivity of remote sensing products to what's happening in the High Plains aquifer. So these are the basic ingredients. Now let's look at your point, Fatih, which is the model reasonable? Okay, is these interaction terms plausible? So to check some of that, what we have done is we have fitted the differential equations by nonlinear optimization of these parameters with some uncertainty bands that are going to come from them, with what was available in terms of data. So we're going to start with the Nebraska case, where groundwater withdrawals are plotted in cubic kilometers per year as a function of time. The data sets that you see was coming from the USGS, and these are shown as circles, blue circles here. And then the model fit to it, yeah, the best fit to it, is shown as a blue line, and the confidence bands, if you will, are shown in dashed lines. And so as you can see, there is no clear peak. Yeah? So there is no stress, there is no Hubbard non-renewable argument to be applied for Nebraska, which is also making sense. And if you look at crop production, you know, it's, again, same idea. The circles are the crop data that was reported. And basically, this is the fit of the set of differential equations to the system that you see here. And again, the crop production here combines corn, sorghum, soybeans, and wheat, and they're reported in tons per year with no distinction. So this actually, interesting enough, by counter-falsifying the fact that the model was developed to try to reproduce limiting resources. It also predicts that when the resources are, when there is no stress on the resource, so it's not acting as a non-renewable resource, the model says there shouldn't be a peak. Okay, now if we go to the central High Plains, meaning Kansas, the story is different. We have already seen that Kansas is not receiving as much recharge, yeah, and the withdrawals are high. So we anticipate that Kansas ought to begin to look, yeah, like a non-renewable resource when it comes to water extraction and grain production. And basically, that's what the data set here says. If you look at groundwater withdrawals in cubic kilometers per year as a function of time, again, the blue line, this is, again, fit to very heterogeneous data sets. But the goal is that the pattern seems to be about correct in terms of suggesting that there is a peak in water, followed by a peak in grain production. Okay? The peak in the water extraction curve is also asymmetric. Okay? So clearly, it is not a Hubbard-like curve just because the symmetry is not preserved. Okay? Unlike peak oil with Hubbard's analysis. And it seems that at least for peak grain, seems to fall after peak oil. And there is a slight decline, actually, in grain production after the peak. And if we look about timing, we expected that the peak water extraction in Kansas was about late 1990s. The peak grain in Kansas is happening about today. not today, the period of. OK, so now let's go to the most troubling state, Texas. So what's happening in Texas is always a mystery. But we are academicians, so we can offer some speculation for you. And the speculation is this, that if you look at the data set from 1960 to 1980, you find that there is, with some imagination, you find that there may be a peak oil, a peak water extraction that has happened. And then shortly thereafter, there was a peak grain production. With the limited data set from 1960 to 1980, it looks like the curve is quasi-symmetric. And then something happens, around 1980, and then we had a rebound in both crop production and water extraction. And the working hypothesis about this rebound is a technological disruption, very much like what happened with oil, with fracking and horizontal drilling. In this case, it's rapid adoption of LEPA. LEPA stands for low energy precision applications. So this is basically sprinklers, drip irrigation, water conserving measures. And what they did is that they allowed actually more grains to be produced for water extracted. Okay? So they did their job. They actually enhanced the efficiency. Okay? But they didn't change qualitatively the boom-bust nature of the dynamics of grain production and water extraction. So this is still qualitatively following the same dynamics, but they did actually allow more crops to be produced for a unit extraction of water. So for the purposes of presenting the results and to try to understand what technological disruption does to the water system, we're going to analyze Texas, at least the model outcomes of Texas that are fitted to this data, in two phases. One we will call the pre-LEPA phase, and one we will call the post-LEPA phase. Okay, so before and after the technological disruption. Are the dynamics of the water extraction and grain production similar, or is there some fundamental shift that has happened? Okay, so is the technological disruption really what the Wall Street Journal likes to think? It's going to be sustained again and again and again. Or is it going to revert back to Hubbard and the exponential growth being unsustainable? Yeah. Did I build the suspense enough? OK, so let's proceed. So to do that, we're going to do what fluid mechanicians like to do, which is present normalized variables. Okay, we don't like units in fluid mechanics. So what we're going to do to put the graphs on the same axes, so to speak, we're going to present the groundwater withdrawal as a ratio relative to the peak, when the peak exists, as a function of time where 0 is the occurrence of the peak. Okay? So this way we can see symmetry and symmetry breaking in the water part much cleaner. Okay? And here's what we find. So let's start with Nebraska. There is no peak, so that doesn't matter. Let's move to Texas in the pre-LEPA phase. So that's the most inefficient irrigation. And so we expect it to look more and more like a Hubbard-like curve because it's unsustainable. The water extraction is so high relative to the recharge. And if you look at the solid lines, these are all model fits. That's why I'm summarizing the model fits without the data. The model fits, you find that actually the model fit is suggesting that Texas pre-LEPA was like a Hubbard curve. It looks like peak oil before the technological disruption. So what did the technological disruption do? In a nutshell, mathematically, what did it really do? Did it fundamentally change the dynamics? No. It did something slightly different. If you look at the Texas post-LEPA, which is in dashed lines, you find that the technological disruption actually, qualitatively, because these are all normalized, so we took the numbers out, the peaks are off. Yeah? What it did is it actually generated asymmetry. So it is a symmetry breaking mechanism. Okay? And now let's go back to Kansas, which was more sustainable, so to speak, even though the extraction rate was very high compared to the renewal. We find the same thing. The asymmetry is increasing. Okay? So now we have some idea of what technological disruptions might do to the water system. Okay? If you have a highly unsustainable extraction, you're going to see Hubbard. As you relieve, basically, the stress on the water system, we will see more and more asymmetry building, but we're not going to change qualitatively the behavior of the dynamics. Fair enough. Let's move to the grain. So this is crop production ratio, very much similar to what we have presented the water side. So they're normalized by the peaks. And once again, there is no peak grain in Nebraska. Maybe that's a hint that we should all move there. I don't know. And then what we see is that if we keep the zero axis for peak grain centered around the water, so this is still where peak water occurred, and now we compare what's happening to both the asymmetry in the grain production and the delay relative to the water. And here's what we find. If we start with the Texas pre-LEPA, which is in solid line, we find that the grain production is also symmetric, so that is somewhat jiving with the water, and the delay is short. Yeah? If we move to a technological disruption, which is Texas post-LEPA, we find that the asymmetry is beginning to break, and the delay is getting longer. Okay? And if we go to Kansas, we also find the same thing. There is more asymmetry and more delays. So that's basically, in a nutshell, what's happening to the grain production, groundwater extraction from a dynamical systems perspective. Now, in dynamical systems, you cannot present a talk without showing phase spaces. Sorry. Or phase planes, yeah? So we have to show those, and we need to understand basically what these delays are doing and what are the implications of those delays for data-only driven approaches, which is very important if you are a fan of data-only models. And here's what you find, is that if you plot the water extraction ratio, so this is, again, water extraction relative to the peak, against crop production ratio, normalized by the peak, again, so we can compare all three systems, yeah, on the same graph. Again, this is Nebraska, no problems, there's nothing there. Now, if we look at Texas pre-LEPA, Texas post-LEPA, and Kansas, we find hysteretic loops, okay? So what does that mean? It means that if you are trying to predict crop production from water extraction ratios empirically, just from data, yeah, and depending on the period that you have sampled, yeah, you could see positive correlations, you could see negative correlations, or you could see no correlations. That's a problem, yeah, depending on the window that you have interrogated. Okay? But if you have a dynamical systems perspective, yeah, you will see why. Okay, so that's the first thing. And again, you see that the hysteretic loop, yeah, the hysteretic loop seems to grow, yeah, seems to grow with the action of the resource becoming less, more and more sustainable, at least in terms of extraction to the extraction rate versus the renewal rate. And just to make that point clearer, suppose you take two functions, x is sine of omega t, y is sine of omega t plus phi. Yeah, you plot x against y for different phase angles. Well, if the phase angle is big, you're going to get a big loop. Yeah, and if the phase angle is low, you're going to get a small loop. So in fact, the loopiness itself is telling you that there is significant lag. Yeah, and that lag has important consequences in how you interpret, basically, the relation between water extraction or correlations between water extraction and crop production. Okay, one last point, and then I will stop. So what causes this hysteretic loops? Now, we have a dynamical system. I mean, what's the point of a model if you are not going to use it to understand in mind-sized bytes what's happening to this loopiness or the hysteresis effect, basically? So now to go back to your point, Fatih, which is the interactive terms. If you break the dynamics into symmetric and symmetry-breaking terms, yeah, meaning that the symmetric dynamics are such that if you throw those terms out in the red box, yeah, you end up with the differential equation dw dt and dc dt are proportional to cw with a negative sign. Divide the two. Okay? If you divide the two, you get actually a differential equation that tells you grain production, annual grain production, varies with water extraction with a negative sign, and it is constant. So that explains the negative correlation that we have imposed artificially in the model construct. Yeah? We have imposed it. Okay? So what is causing the loopiness then? So that's the negative, that's the line, if you like. What is causing the loopiness? Well, it's the symmetry breaking term. More interesting is that if we're thinking about projections, especially for Kansas and Texas, where dA dt is 0, the symmetry breaking terms is the recharge rate, yeah, and the depreciation rate. So these are the two important terms. Now, let's think a little bit more about this. Suppose we decide that we're going to see what happens at equilibrium. Okay. Well, at equilibrium, dw dt is 0, dc dt is 0. By the way, the dynamical systems people talk about steady state and equilibrium interchangeably, even though thermodynamically they're not. Okay? But that's another conversation. So in this case, we are going to set this term dA dt to 0, get rid of it, so that would be a complicating term, but it's not as relevant for the states we are concerned with. And we try to calculate the equilibrium value for the water budget and the equilibrium value for the annual grain production. And here's the kick. If you do that, you find that the equilibrium value for the water budget is K3 over K2. Now, K3 and K2 have nothing to do with the water budget. Go figure. It seems that the equilibrium value of water doesn't even see the recharge. How could that be? Okay? We'll come to that in a minute. That's what the math says. I'm not making this up. Okay? Now, in the C equilibrium value, well, you still recover an inverse relation with the equilibrium value of water, but that's cheating. That was almost by construct. However, you find that the equilibrium value for crop production, or annual crop production, does depend on the recharge. Go figure. The water is not, but the crop production is. Okay. Now, this was a puzzle. I was clearly, at the beginning, I thought, man, this is a major, this is a major theoretical embarrassment almost. So why is that? And it turns out that that actually happens a lot, more than what you would think. And that's basically referred to, again, in population dynamics. That was kind of the inspiration of this work. And there's a technical name for it. It's actually called the paradox of enrichment. Yeah? In the predator-prey system, you try to make the habitat of the prey better by increasing, let's say, its food, its habitat. Ironically, you end up making the production, making that enhancement to the ecosystem or the food sources for the prey. You end up actually increasing the population of the predator, and that was basically the paradox of enrichment. And in it, if you try to make the prey population better by increasing its recharge rate, R in this case for our water, it ends up paradoxically increasing the predator population, in this case, grain production. So it has no impact on the water. It turns out to be impacting basically grain production. And that's a surprise. It's not the only system that exhibits it. There's a lot of talk in climate change using the miracle of geoengineering. And the first tests that were done, let's say in a similar setting where the ocean itself, in areas of the ocean where there was, how should we say, fertilization demands to increase carbon sequestration by phytoplanktons. Yeah? So experiments suggest that if you go there and you throw nitrogen or iron, whatever limits the phytoplankton, there was a big surprise. In fact, the CO2 sequestration didn't go up. Actually, it went down. Okay? Why was that? Exactly the same mechanism of paradox of enrichment. Actually, what happens is that if you increase the population of the phytoplankton by increasing the limiting, so to speak, limiting resource for them, you actually end up increasing the population of the zooplankton, which is a predator, yeah, on the phytoplankton. And so if you're thinking that if I enrich, the phytoplankton will sequester CO2 and then sink to the bottom of the ocean, yeah? By doing so, in fact, there is a risk that the zooplankton will try to meet the phytoplankton near the surface. It's always easy to meet in 2D compared to 3D, you know? Yeah. And so basically, that's where the zooplankton are going to be hanging around. And those tend to respire a lot after they digest the phytoplankton. So that's the problem in a nutshell. So it's called the paradox of enrichment, and it pops up a lot. There are also variants of it in different contexts. If you are into energy efficiency and energy production, it's known as Jevons paradox, very similar argument to this. So it appears in traffic engineering, plenty of examples where you build a road to connect point A and B to thinking that you're going to somehow reduce congestion, you end up increasing congestion. Okay, so there are always unintended surprises or unintended consequences in complex systems where if you adopt a linear thinking, about cause and effect, you might actually create a worse setup than doing nothing. Okay, so with that, now I'm going to negate myself and offer a prediction contrary to what Papert said. And here's the predictions for groundwater-based crop production in Texas, Kansas, and Nebraska. And just for reference, I've shown the values in 1980, 2016, and the forecasts are in 250. So for groundwater-based crop production, we find that in 2050, there will be a slight decline relative to 2016 in Texas. In Kansas, there is also a slight decline, but still better than what was there in 1980. And in Nebraska, there's just a very rapid growth. So these are the model projections, even though Seymour Papert said, don't do it. Okay. Now, future outlook. This is not my area, so that's why I'm going to recommend them. And I figured Dara's in the room. He can answer all those questions. So can we use these types of simplified models in conjunction with some remote sensing products? And I'm not an expert on this topic, but it is too tempting not to put this slide, okay? And basically, there are two major advances in remote sensing. Some of them are impressive engineering feats. The GRACE satellite that is able to monitor groundwater at very large scales. And in fact, if you look at the GRACE data where the High Plains aquifer is, you see that it is actually gaining water. That, I think, is thanks to Nebraska, not Texas or Kansas. If you look also, so this is one way we can think about groundwater dynamics. If you look at the MODIS satellite, well, it can provide you with greenness indices, like the leaf area index. So if you couple that or marry that with some smart algorithm that can tell you crop type based on these leaf area dynamics, there is a chance now to see some aspects of grain production. So we see that there is at least the blueprints of two satellite products that feed directly into this type of dynamical system, and that's the beauty of these simplified models. Whether it can be done or this is accurate, I have no clue, okay? Ask Dara. Okay, so like all models and all theoretical frameworks, there are certainly model limitations that need to be flagged. And so the more important one is extending these dynamical systems to include both surface water and water quality. Those have been neglected. There is certainly a role surface water plays, more so in recent policy debates of combining groundwater and surface water, where you could store some surface water in the ground and use it later is important. Water quantity is another big issue, and that is certainly the case in areas like the Indus Basin, where water quality is major. Now, if we were to think about the associated satellite products that may come to support this type of analysis, the swath satellite might provide some information on surface water. I have no clue if it is accurate enough to do that. But at least there is a satellite product out there with some nudging and some plumbing. It might do something. For water quality, as far as I can tell, it's very restricted. There is some chance that salinity maybe could be discerned, but that's about the limit as I could see from not doing any research in this topic other than just looking at the literature. Now, why am I interested in these two? Initially, when this work was being done by the graduate student Asad Murad, I was hoping for three box models for the simple fact that I was actually looking for chaos in the analysis. And Asad said, I need to graduate, sorry. Let's start with the two system model, and then you could ask another graduate student to extend it to 3D and include all of those. But that is certainly true. If you add surface water or you add water quality into this mix, there is a chance that under certain restricted conditions, you could get chaotic dynamics, okay? Which is, at least, they do require 3 ODEs at minimum. And so analogies that may be drawn to the Rosler system or the Lorentz system might pop up. And I'm going to finish this talk with a shameless advertisement to a new journal called Geophysical Research, ARC Geophysical Research. And I know many of you would argue that we don't need a new journal, okay? But I think we need a new publishing model for journals. Models where they divorce money flow from science information flow, okay? And basically, we attempted to do that, primarily the work of Casey Miller. What Casey did is he convinced the provost of University of North Carolina to put a pot of money as an endowment to University of North Carolina Press, which is an independent entity. So it's a private company that services University of North Carolina, but is not owned by University of North Carolina. And basically, the premise is that with this limited amount of resources, we can hire 2 staff members that can deal with the submission issues, and they can also allow us to administer the servers and have an open source access that allows editors and authors to use basically the Janeway system for submissions and reviews. The editors at this moment are Diogo Bolster, Paolo Dodorico, myself, Greg Lawrence, Paula Passalacqua, Tamlin Paveski, and Daniel Tatrafosky from Stanford. There is another unique thing about this journal is that it has a distinguished advisory team. So we get to be hammered every year by people like Effie Fufula, Li Luang-Fu, who I think got his PhD at MIT, Bill Gray, who has a long history in publishing. In fact, when I was a graduate student in 1990, I was reading papers by Bill Gray in 1970, okay, published in 1970. So long history and experiences in publishing. Dennis Lettenmeyer, Casey Miller himself, who initiated this whole thing, Mark Parlange, Andrea Rinaldo, and Isabella Velliconia, more into the remote sensing and ice sheets. So there are plenty of editors-in-chief, as well as distinguished advisory teams. And we hope that this can work. It is free to publish, free to read, so there is no cost to authors or readers. And more important, scientists own their science. There is no copyrights, okay? So when you submit a paper, you are not filling a copyright form. So I will leave it at that. I'm happy to answer more about what we have found in a more in-depth analysis, but that's basically our first attempt to decouple basically money flow from science information flow. And with that, I will stop. Thank you.
For the wonderful talk. And just before opening for questions, I'll give a reminder that after this there'll be a reception with nice food and so on. So please stick around after for further discussion. But yeah, questions from the audience.
Yeah. Oh, sorry, Heidi. Yeah.
Oh, okay. Go ahead, Heidi.
Gabby, that was really a great job. You're a great speaker. I would love to take a class from you someday.
Oh,
That's the highest praise I can give someone. My question is, in the 2050 prediction for Nebraska, I mean, it's a huge jump up.
Yeah.
Is there a hidden assumption about land availability?
Yes, of course. That assumes that the aquifer is accessible, and so DADT is growing as.
So what if you actually added the constraint of land area?
I mean, it is. So this is the growth that we are seeing. So it's still available. I mean, I don't think in terms of surface area we didn't even come close to a huge.
The assumption is that you will keep expanding the farms.
At the projected rate that you see. So in fact, it's beginning to flatten. If you look, you see that initially it was much higher than at a later time. So by 2020, yeah, we are somewhere here. By 2050, if you add 30 years, it will begin to flatten out.
Okay, so that's not an element. And then if I disagree.
But you could also add a constraint. I think this term is not the biggest term. Okay. It's the recharge rate that is really the biggest term. Comparing the two is.
My other related question is, I mean, what about the constraint of like how much grain we want?
So that would be the economic feedback. Okay. So that would, in a nutshell, Heidi, this would have appeared in the parameter that describes. Let me go back to the model. I mean, the beauty of this simplified model is this. It would have appeared with a K3 drop. Yeah.
Okay, yeah.
So, and this is really coming by saying, you know, if there is a lot of depreciation, this term will be big, and that would put a limit on the growth. So if the so all the economics and the market forces, yeah, are in K3, but they're there. Yes.
I'd like to follow up on that because I'm interested in the same issue. One of the things that seems to me is that the Hubbard analysis had a carrying capacity right in the equations.
Yes.
And that has tendency to damp the growth.
Right, the finite resource effect,
And
basically.
I wonder in Nebraska, the carrying capacity is not just, it's not like if you've been to Nebraska, there's a lot of just barren land that's waiting to be cultivated. It's got huge amounts of corn, maize, which are,
Right.
a lot of it's for energy, not for energy production.
Good point.
For,
Yeah,
not
food.
for,
Not food.
for feed.
Yeah.
So I wonder if in order for Nebraska's agriculture to grow,
Yeah.
that the crops you looked at have to replace other crops.
Exactly.
Maize, I don't remember whether maize was one of them.
It was. I mean, the majority is still corn, but yes. So if the crops were corn, sorghum, soybeans, wheat, and I think there may have been maize. It was not a big fraction, I would say, perhaps from the analysis.
Maybe the economics between those is.
It could be important. I mean, if you want to develop a detailed budget, you could have a budget for each one of them, and you could look at interactions and transformations.
But I
You
don't
know,
think you
yeah.
kept them together, but
Yeah.
I just wonder how it would change Nebraska if you put a carrying capacity and thought about within the field limitations of nutrients and light, and not just the fact that there might be more land to go
Sure.
into.
No, I that's.
It seems pretty steadily developed for agriculture.
Yeah, I mean, so the growth was coming from this. But even if you remove that, the reason Nebraska, at least in the eye of this model, whether correct or not, the reason Nebraska is high is primarily the recharge rate. It's huge if you compare. Sorry, let me go back to that. To the measured recharge rates. This is what is causing it so far.
Yeah, but here, actually, Gabby, when you go to the north further to Nebraska,
Yeah.
the equation you have does not have discharge into streams.
But that's the point.
And-
I
and
wanted
I
to do that.
Yeah, and I wonder if that's an important component.
It could be.
And it would do a negative feedback.
It could be. The question is are the streams just a buffer? So you take away, you store in groundwater, then you give it back to the stream. So on long time scales, remember that these are model calculations that are running on 5-year. The crop production is a 5-year cycle. These are not event-based. They're very far from events. I haven't even varied the recharge in time for 50 years or 100 years. Okay, it was strictly designed to show the basic elements of a model like this. You could complicate every single one of them. You could add the recharge. You could add different stoichiometry. You could add different energy. You could add uses for the crops. Some go to food, some go to energy production. So there may be other economic feedbacks and other depreciation terms that would pop up. This is all viable. All I wanted to say is that with this level of simplicity, you still see the patterns. They allow you to take a messy data, and you begin to see some patterns emerge. Not perfect, but some patterns are beginning to emerge, particularly related to a Hubbard-style analysis of peak. I completely agree. I wanted to do this. I was itching for adding more variables to generate more degrees of freedom in the dynamics. It was
One other more important thing is that the productivity of agriculture has been changing very rapidly in this region over this period.
Yeah.
So during the 20th century, a factor of 4 increase. So what that assumed, you emphasize the technological disruption, the water efficiency. But what about, better seeds, better fertilizers?
No, for sure. You have to enable that. So here's an interesting result, and I didn't show this because let me show you one thing about the coefficients that were fitted. So if we compare, so this is the dynamical system, Fatih. Yeah, let's compare Texas, pre-LEPA and post-LEPA, because that's a big change in efficiency, whether be it water delivery or let's say nutrients availability. The depreciation term is going to be the same. Yeah. So let's look at Texas pre-LEPA and look at the depreciation coefficient K3. Yeah, it was in the pre-LEPA phase 0.075. In the post-LEPA phase, it is 0.046. This is what is allowing you to support way more crops per water extraction. So this is evident when you break the model into these two phases. I think if you add nitrogen efficiency, sure, the crowding effects might generate a K3 that is going to be bigger. So again, it will be there. It would appear in that. You could, of course, add more complications. You could add some competition at the farm scale. this assumes it's all economic forces, but it could be done at the farm scale. You could say there is internal competition. If I try to keep the land constant but add more crops per unit area, my productivity will go down. For crowding purposes, again, the same thing. Adding nitrogen fertilizer might enhance it up to a point, but then you get this crowding effect.
Okay, lots of questions. Maybe we'll only take one or two more, and then save the rest for the reception, hopefully. So I'll leave me.
Are these systems coupled in any way, or are you making approximations that you're decoupling them?
No, they're completely coupled through the interactive terms. So to solve C, you need W. To solve W, you need C.
No. C and W, I understand.
Yeah,
but
yeah.
in these different W's.
Yes. Yeah, so each is solved
in principle,
separately.
You could make a compartmental model.
They are compartmental by the state itself. So we are thinking about Nebraska, the area that is available for irrigation.
Well, what I'm saying is you could put a network.
Oh, yeah, you could connect them. And and that was one possibility. But that connectivity, if it is not happening hydrologically in the aquifer itself, it could happen through shipping.
Is it physically happening or not?
I mean, I honestly don't know how connected this aquifer is. It's a huge aquifer. So to what extent, groundwater withdrawals in Nebraska are affecting water levels in Texas? I don't think water is flowing. Because, it's,
There's no physical evidence that they may be.
They may be that connected, let's see, at that level, okay? But I may be wrong.
Yeah, so maybe one last question. We'll take it from a student. Go ahead, Ernie.
Yeah, very interesting to learn about the predator-prey. You motivated the whole talk on sustainability development and shed light on, let's say, economy growth with exponential growth. Do you think this model only applies for variables that have a natural constraint, where the money value is not like a constrained quantity?
I would say the imbalances between extraction and replenishment is what is dictating the sustainability behavior, which to me is a summary of a Hubbard curve. Okay.
But let's say like money is not like the prey variable, right? You can't use something that is unconstrained as the variable to predict economic growth, for example.
Yeah. So if you think about systems that have, so I guess you're asking about Hubbard's analysis per se. So suppose we think like a Wall Street hedge fund manager, okay, where we envision that the acceleration, grows with the resource. Yeah. So if I have, which is how they think, right? I mean, it's usually not the growth rate, it's the quarterly change within the quarterly of the growth. Yeah. So if we think about acceleration, say if you take a process that as a differential equation generically is dx dt is proportional to x raised to some alpha, okay, where alpha is bigger than 1. Okay? So the acceleration is also dependent on x in this case rather than being constant, or 0. This system will exhibit finite time singularities, meaning that you are going to go to infinity in finite time. This was done by von Forster in 1960, beautiful paper. It's called the Doomsday Equation. And that was about population growth in this case. The argument is that, well, every time human population has reached, quote unquote, some critical phase, technological breakthroughs have enabled populations to continue to grow. Okay? So that was von Forster's analysis. And actually, he called this the optimist scenario. There is also the pessimist scenario, which is the fact that the carrying capacity of the planet is degrading, and therefore, we are actually going to support less and less people as time progresses. And he says, okay, well, let's compare the optimist and the pessimist. And he wants to give the benefit of the doubt to the optimist. So he says, in one case, I will have exponential growth. In another case, I should have power law growth. If you look at the human growth population, say from 1 BC, let's say, to 1950 or 1960, it looks like a power law growth, not an exponential growth. So that eliminates the logistic argument, which is essential, basically, to Hubbard's analysis. The interesting thing is that if you continue along this trajectory unimpeded, so there is no brakes that are going to slam to stop the acceleration, you get explosion in finite time, which, according to von Forster, happened around 2028 or something like this. Now, it should be happening now. Okay, which it didn't happen. Okay, but the interesting analysis, of course, in the case of von Forster, he was showing that systems that have power law acceleration, or velocity acceleration that scales up with an exponent bigger than 1, are likely to exhibit explosion finite time. So what does that mean, per se? I mean, there's no infinity. What does that really mean? It means that the dynamics that was describing the regime before the singularity is not going to be the same as the dynamics that was that will explain the regime after the singularity. So there is a regime change, to borrow from the political science people. We need regime changes. So the dynamics have to exhibit regime change at that point, or close to that point. There were interesting additions to this analysis done by Didier Sornet, where he suggested that if the exponent is complex, gave no reason why it should be, but if the exponent is complex, you basically cheat. You no longer have a first order or a first order dynamical system. You really have a second order dynamical system if you add the complex plane on top of the imaginary plane. So sure, you could get oscillations. So what he found is that you get oscillations around the power law, and the frequency of these oscillations is increasing. Okay, so he viewed this as another evidence of finite time singularity. And why am I saying this to your answer in a long way? Because he analyzed speculative bubbles. Okay, he's making a living out of speculations of where bubbles are going to emerge and crash, basically. And he proved that those types of bubbles exhibit exactly the type of finite time singularities that this type of analysis will not see. So there, the view, if you like, is that when you remove these carrying capacity limitations, what remains, if you have a growth that is not linear, you will get finite time singularity. And I think people who studied city growths, same thing, same arguments. If you look at city growth, number of people in cities as a function of time, they are growing hyper-exponential, and the only way to suppress it is to continuously to invent technologies that make the cities run more efficiently. Same arguments. It's in fact von Forster's argument in a nutshell.
Okay, well, let's thank Gabby one more
Yeah.
time. Is that on behalf of the department? Thanks so
thank
much
you.
for
Thanks very
joining
much.
us.
Thanks
Yes.
for having me
Thank
again.
you.
Yeah, that was fun.
Excellent. Okay, and stay for the reception.